I see questions been coming up already. Any further questions from on Viv's presentation? Joachim?
Yeah, I would like to understand more about the neutrino, the structure of the neutrino. It didn't come out in the presentation, and it was not presented earlier presentations either.
It was presented in my earlier lecture, the last one before that, but basically it's a plane polarized photon that has a mass about 10 to the minus 4 eV per c squared, and that's determined by the fact that it takes, when a neutron starts to decay, it takes about 10 to the minus 10 seconds to decay, which is the time period, which is assigned as the time period it takes to emit the neutrino. And the other thing, of course, is that if you want neutrinos are detected about a second after photons from supernova events. And the only way they can do that is they must have such a small mass that when they travel 10,000 light years or something like 10, 20,000 light years, their mass must be so small that they arrive about a second after the photon. And that also comes from having a mass of about 10 to the minus 4 eV per c squared. Can you turn your phone on, please, Joachim?
You're muted, Joachim. And Pete, also, could you turn
sorry. I mean, the plane polarized photon, can that have intrinsic spin, or is that always zero in a neutrino then?
So the plane. Yeah, my hearing's not as good as it used to be, and my computer's a bit old.
You said that the neutrino is constructed from a plane polarized instead of a circular polarized photon.
Yes.
And that doesn't have an intrinsic spin, right?
That's right. Yes.
So the neutrino has no intrinsic spin, but it has an external spin, and that is the rotation around it. Okay.
Yes.
I got it.
And the other thing that, if you missed it, the other thing about a neutrino, normally I've said that under the theories, plane polarized photons rotating were less stable than circularly polarized photons because of the reinforcement of charge, and also the extra spin h bar of the photon is also its angular momentum, which is an exceedingly powerful force. The neutrino has nowhere else to go. There are no stable levels behind it. Stable levels under it. I mean, it's just got nothing it can decay to. So although it may not be as stable as one would like, it just has no stable level to go to. It's already 10 to the minus 4 eV per c squared. Its temperature can.
Yeah, the lowest quantum state for a plane polarized photon.
Yeah, it's just nowhere else to go.
About that, I have another question. When you have a high energy neutron or proton, and it deaccelerates, it has to deaccelerate in speed jumps every time it emits or sheds a photon, right? So we'll be able to see those speed jumps, or?
So speed.
Because every time it sheds the outer layer of its oscillation and goes into a lower speed, it has to lock to, so it's still self-confined after one wavelength. So it has to go to a certain lower speed. It can't take any lower speed.
It's a process of stopping that emits the various photons, be they rotating or linear. They're not emitted automatically, because even though they're at high energy, and the masses of the muons, instead of being 1/9 that of the proton, their masses would be 1/9 1/9,000th or 1/9,000,000th. Sorry, 9,000 or 9 million times the mass of a proton. So yeah, 1/9 times a million the mass of a proton for TeV accelerations. They don't. It's the stopping that causes all the reactions. The others won't occur naturally because their time zone and masses match up. I said that you can detect that by looking at cosmic ray protons. They've been traveling for thousands of years, tens of thousands of years at these very high masses, way, way beyond anything that we can get in particle accelerator. They remain stable at time.
Yeah, but Joachim, what you're saying is not correct. The thing doesn't stop. It's not a quantized shedding of energy that happens. The energy is continuous of a high energy particle, a proton or a neutron or whatever else. What usually happens in an interaction is the interaction takes place. You can have multiple small interactions, bremsstrahlung and so forth, which are emitting photons, and that will be gradual. And it can be at any, well, it'll be small energy losses with that. But the big energy losses, where extra particles are created, happens when something hits something else. And in that case, what happens is both the proton and the neutron fragment, or whatever's been hit and whatever's coming in fragments, and in a strong interaction kind of process. So then you get a lot of particles arriving from a single event. So it's not that it's not that it has a series of quantized levels of velocity. The velocity is not quantized. It's continuous. If that's what you're asking.
So when it sheds a Bromsstrahlung photon, what kind of photon is that?
Well, it's a photon that has to do with a thing going through a medium. So you're going through an electric field medium. You're going through a particle medium. So they're relatively low energy photons. Use it as a detector. So compared to the energy of the total mass energy of the particle, it means, as you know, break radiation. So that happens when the particle's going faster than light. It's a shock wave, a light speed shock wave. So you have.
But isn't
that Cherenkov radiation? No.
Yeah. Well, yes, that's right. Sorry, I'm getting mixed up. Yes, quite right. But bremsstrahlung.
But doesn't that mean it has to be quantized? Because if it, all right, bremsstrahlung, you usually do an experiment where you actually you rotate an electron or a charged particle around in a magnetic field, so it never actually breaks. It just changes direction, right?
Oh, that yes. Well, whenever a particle changes, charged particle changes its direction, yes, it has to emit a photon. Now
it's not breaking.
That's not breaking radiation.
Yeah.
All of the photons emitted by whether it's from going around the path of the accelerator or whether it's actually stopping, they will all be circularly polarized linear photons.
Thanks. That's what I wanted to know.
Yeah.
I missed that last statement when you said that they're, in certain cases, they're always circularly polarized photons. Your last sentence, I didn't understand what you just said.
So when the bremsstrahlung and the radiation coming out from photons traveling or protons traveling around in particle accelerators, they will always be circularly polarized photons. All photons emitted by particles, whether they're gamma rays, infrared, soft X-rays or whatever, they will all be circularly polarized, and I suspect that comes because the object that is emitting them is making two revolutions within its wavelength. So the photons start out, well, the photons are emitted from something that is already turning.
Mm.
I guess it has to do with that you accelerate the charge away from the direction it was moving, and it has to compensate for that rotation. I'm thinking about you can also break the charged particle by having I'll show you. You wiggle it, and then every wiggle, I don't think that even has to emit a photon, but a total of many wiggles can emit a photon. I'm not sure. And that wiggle, then it actually breaks the particle, not accelerates it away from its direction. And that maybe doesn't have to be circularly polarized.
I think this discussion about the polarization of photons coming out there is, remember, there are 2 degrees of freedom of polarization of photons. If you have, so the physical processes that are happening is, one is there's a shock wave appearing because you're going faster than the speed of light. Another one is that you have sort of small angle scatterings, which are just electromagnetic scatterings that can be multiple and will have a very wide frequency range and not a particularly well-defined direction. They could be in any direction. The other one is if you have a particle exchange where you actually hit something pretty heftily, in which case you can start smashing things up. And the other one is where they hit each other with a strong interaction if these things are strongly interacting particles. In other words, the 2 particles actually overlap and then they smash to pieces. So, but all of those things are pretty, well, except for the Cherenkov thing, which has a very well-defined angle as it comes through, depending on its velocity. They're all pretty chaotic processes when these things happen. They're not going down like a series of quantum steps, as in quantized systems in the solid state. So,
but I guess it has to. The sum of all energies has to be those quantized states that you can shed.
Joachim, why do you think it has to?
Because every time assume it runs at half c, a particle, you got it accelerated to half c,
yeah,
and then you shed the outest layer of it so that its clock goes faster by 1.
No, but wait a minute. When you're talking about these kinds of radiation, I mean, we're talking about Bremsstrahlung. We're talking about something which is scattered electromagnetically with something.
Bremsstrahlung,
yeah, we're talking about charge-charge interactions. This is just a charge-charge interaction. It's not shedding a piece of its nature. It still remains the same. Just proton goes to proton.
Yeah, okay. But
yeah.
So I'm kind of imagining that what I'm trying to, when you break it in the direction it's moving, when you have that break emitting a photon, that photon will be emitted in the other direction, not in the direction it moves, right? Okay.
Yeah. I think when Joachim's talking about,
I'm too far. I'm going to be silent now.
I think it might be a semantic issue. I think when Joachim talking about quantization, are you talking about the fact that when these things are winding down their resonance, they're resonating down from like higher standing wave energies to lower standing wave energies, so that the amount of energy that they emit has to be the difference between those 2 states, which would correspond to the different the sub-resonances within the particle. Is that correct? Is that what you're asking?
I'm thinking about when you have a high speed, its clock goes down, and then you break it down, its clock increases, and then it has to snap together at a certain lower speed. It can't go to any lower speed.
The thing is, its own rest frame, its clock remains the same. The thing maintains its integrity until it loses it. So if it maintains its integrity, in other words, it's a proton going to a proton plus a photon, for example, or X going to X plus gamma, whatever it is, it's maintained its integrity. It has merely lost speed. And it can do that by 3 or 4 things with 3 or 4 low energy photons with glancing hits, or it can do it with one bigger one, but it can do it with any energy from any energy continuously. This is a continuous process. And the spectrum of that radiation is continuous. It's very, very good.
That's what I feel. It's something wrong with that. For me, it feels that it can't be continuous because it has to shed its energy in quantized step to be able to lock to a higher clock rate.
Arnie, any chance you could put up slide 10? because that's yeah, it's not actually a continuous process. It's a step-by-step process. As the yes, that one, thanks. You'll see there the various particles on your on the left. They have they don't continuously go down. They emit some energy and go down to the next level, and that energy is not just a pion or a muon. It includes some gamma rays as well. But yes, so in that regard, each of those steps down is quantized as they're cascading their way down.
Yeah, and that's the quantization I'm trying to understand, where it originates from within its internal rotating photon when it snaps to the next lowest speed it can have. That's what I thought. Because it speeds up its clock when it slows down its speed.
Yeah. I would leave it up to myself. I would just leave this up to particle physicists who were interested in that. I mean, they've been looking at it for a long time, and there are a lot of theories about it.
If you go to slide 13, I think there is a lot of research that can be done on that to explain what everything they see and all the transitions they see there, what actually are the particles shedding there, what is the neutron and proton actually doing there in every shedding.
Yeah, I think that there is quite a lot of work, if particle physicists were interested in it, to go through and analyze all of the 200 or so that they've detected in terms of this theory.
Well, Viv, you might be in luck. I just saw an article that CERN just announced that they're spending 21 billion euro on a new 100-kilometer long collider that they're going to build in order to understand the Higgs boson.
Oh, well, poor old Higgs boson, no matter what, it still decays back to photons. I think we should send them a copy of this talk and say, hang on, I'm going to have a look at this first.
Before you start building, read this paper.
Yeah. Save yourself $100 billion. Read this paper.
We have more important things to do.
Yeah. And I think they only want to do that because the Chinese have announced that they're going to build an accelerator to generate Higgs bosons at about 40 times the rate that CERN could. So,
I have a question.
Yes, go on. Oh, yes, Wolfgang.
Wolfgang, I think it's a great talk, and if I were to quickly summarize, basically, I think what you're saying is there are very few stable particles, and all of the high energy field can be understood by excitations of internal states of those particles, and therefore what we're getting out is the transitions between fundamental states of those particles that you mentioned, electrons, protons, and so on. Underneath all of that stuff, you have a rotating electromagnetic field concept that moves as a photon and can be captured in a stable configuration of a particle. My question, and I think I've sent you several emails on this, is how is mass and charge or the gravitational field integrated into this picture?
Well, mass, photons have mass. I know there are.
How? Why? How?
You
can't just say energy is the same, you know, that's fine, and that's what someone said, and if, you know, that energy is the same as mass, but how does your, I love the fact that there's a double cycle in your model, but is there some, I can understand a self-contained electromagnetic thing because we have superconducting rings and so on and so forth, but there's always mass holding stuff together in any of these experiments. And
in Vivian's model, you don't necessarily need to talk about mass. It's enough to talk about energy of the rotating field. Right? You don't have to talk about mass at all, Vivian.
Well, yeah, you can always abstract it into this energy concept. I abstract it into action. Action for me is the fundamental. I mean, every time you say a spin, H, you're talking about contained action, activity. But somehow visualizing this, understanding this, for me at least, requires some place where charge and mass, which is what we fundamentally grab and see, has to be there somehow. And that's what I'm kind of looking for now. And I believe that the containment process requires some addition of a mass field that is intertwined and self-contained with the electric field that you're containing. So
I don't think you need that complexity. The fact that the photon is going around perpendicular to the direction of motion means that it can't go at the speed of light, and that property is what's giving it mass. The mass is the thing that stops you from accelerating it, and you can't accelerate something to the speed of light in one direction, or even substantially, without the thing that's going around in a circle perpendicular to the direction you're accelerating it. So you don't need any additional field like the Higgs field. The very fact that you're going in two directions perpendicular means you cannot go at the speed of light, which is mass.
Basically, that you're right, Pete. I mean, what happens is that the relativistic corrections don't apply for mass, don't apply to a photon, but when the photon then turns around and travels in that circle and moves, travels as it's moving, it travels at the speed of light, and it's that which gives the properties of special relativity corrections. As far as mass, do photons have mass? An electromagnetic space is storing electromagnetic energy. I mean, photons have been known to have momentum, and it's very difficult to find, and it's been measured. It's very difficult to find any theory where something can have momentum without mass, or any theory that would stand up for scrutiny anyway.
I think there's a talk at cross purposes here, because really mass is two different kinds of things. You have rest mass, and you have mass due to energy. Now, any energy is defined in any system, and if one wants to look at the proper mathematics of this, just look at Martin's most recent papers up on Quicycle. Can be weighed. Light in a box, although light is rest massless, can be weighed, and the reason is that light blue shifts and red shifts in the gravitational field. So if you imagine it moving up and down inside a box, as it moves up, it red shifts, it hits the top of the box, red shifted. As it moves down, it blue shifts, it hits the bottom of the box, blue shifted. There's a momentum transfer on top and bottom, which means there's an effective mass given by that momentum, over hitting the bottom, pushing it down more than hitting the top and lifting it. And that amount is exactly mc squared of energy, or corresponds to the energy of the photon, where the momentum of the photon is given by E over c. So this has been long known. I mean, this is a question that I solved in my undergraduate degree in the final year. So it's not a hard thing to do to get that kind of mass that you can weigh from momentum. It's a well-known problem that has been solved a long time ago. However,
John, I think Wolfgang want to also have a grip on the action you get from the particle on the tension in the space-time.
I was just
gentlemen, there are too many microphones on. Can we all put them off except when we're talking?
Yeah, I was just coming to that partially, if I understand you correctly, Joachim. I mean, the thing is that one does still need a binding force. One needs to understand where charge and the mass, how the mass interacts with the field, and one needs to understand where the charge comes from. But that's exactly what Martin and I turned our attention to back in the 90s, and managed to derive the charge from the angular momentum of the photon. So from that point, and there, the thing that's confining the photon is the interaction between a rest massive scalar field and the electric field. So that's the thing which is providing for a rate of momentum which is not just linear, as it is in the case of a photon, but going round and round in circles. That's, within my model, the thing confining the photon and making it go round and round in circles. As it does that, it necessarily, equation 1 in the set of equations that I presented in QC0001, for example, produces the charge. And that charge can be calculated, and it's close to the elementary charge. So given that as a starting point, then what one can move on from that and say that any of the confined energy, light speed or otherwise within the system, contributes to the total rest mass of the electron, which it does. And if you look at the Dirac solutions, what you see for the solutions in Dirac is you see precisely something which is going backwards and forwards at the speed of light. There's a light speed oscillation, there's a Bewegung, and then the whole thing moves. And that movement is exactly the linear momentum that one would measure in Newton's terms, a half mv squared of energy. So if one looks at the series expansion of those things, one sees the mc squared term plus the p squared over 2m term, the half mv squared term, as both coming out of solutions of the relativistic quantum mechanics equations. So these things are all internally self-consistent. This is not some magic mass that's appeared from somewhere else. This is a mass which is inherent in the fact that one has confined energy. Confined energy could be anything. It could be photons, it could be heat, it could be matter, material particles. Whatever's producing energy can be weighed and is weighable, and hence has a gravitational mass and presumably then also an inertial mass. So that's where the mass and the charge are coming from.
Can I?
Yep. Okay.
Yeah. So in Vivian's talk and in Vivian's, I think we will see it throughout. He doesn't need to mention mass at all. He only needs to have the particle itself to slow down its clock when it goes to higher speed. And that is kind of it behaves like a massive particle, but it's just because it needs to get self-confinement that way. But there is a secondary effect that it actually tore. Can I just continue that? It's a secondary effect that Wolfgang, I think, is after also, that it changes the gravitation field around it also. And that's not part of Vivian's model, and that's part of your model. And how can you talk a little bit about how the massive particle actually affects through this mass field, root mass field, the coordinate system, the X, Y, Z.
I think this is a misunderstanding. I mean, there are two different things going on. One of them is a first order effect, or even a zeroth order effect. That is the effect on the momentum. So one has two momentum terms. One has a PE term, a scalar times the electric field direction, and one has an E cross B term, which is perpendicular to that, which is the standard Poynting vector, electromagnetic momentum. So those two things contribute to the momentum and get you going round and round in circles. Now that's not a gravitational effect at all. It's not a distortion of space-time. It's two fields which exist within space-time, both which are of space-time. So confusing that with, it's not a gravitational effect that's making things go round and round in circles. It's an extra scalar mass term which is providing that extra momentum term. So it's not gravitational. Now, gravitational is another force. I'll talk about that later. I'm going to talk about gravitation in a later lecture as to what that might be. But you know, we're making up models as to what those things, as to what gravitation may be as well. So, but we'll come to that in a much later thing. There's two things are not to be confused. And when you're talking about mass, one really needs to always distinguish. We really should have two different words for this: rest mass from the total particle mass. Anything that contributes to the energy contributes to the mass of a particle, to the weighed mass of a stationary particle. Rest mass is something quite different. Rest mass is something that happens when the particle is at rest. The rest mass of a photon is zero, because if you bring a photon to rest, it has zero energy and it just redshifts to oblivion. In the case of an electron or so forth, you always have a residual mass because the thing needs the intrinsic interaction that it has with the rest of the universe to be balanced. So It's a continuously interacting particle with all the other particles in the universe, and that has.
I remember 20 years ago we met in a hotel in Germany. You had a vision of that field that you get from a particle that is very intense energy in localized space as absence of space. It doesn't tend. It doesn't.
That's right.
It doesn't twist the space. It removes space. Is that what you have in mind now also?
That's what I have in mind for gravitation, but we haven't really discussed gravitation yet. So that's going to require a talk and then a discussion of that aspect of But yes, that's my view of how gravitation.
And that's what the view I have of the root mass energy term, that it asks that the strength of that absence of space that you invoke.
Well, I think that view is incorrect. But to concatenate those two things as being the same thing is to say two different things are the same thing.
And that's what I think it is.
Well, okay, but you're welcome to think that, but I don't agree with that. So just to be clear, I think what's happening is thing goes round and round in circles, and then there's a bit of space missing. Now, the round and circleness is not created by the bit of space missing. It's the other way around. The bit of space that's missing is created by the fact that you have a piece of space which has a photon going round and round.
Yeah. It's a hen and egg situation, but still, it's a lack of space for the environment around it.
It's not a chicken and egg situation at all. It's like a grain of sand on the beach compared to a dinosaur situation. One of them is completely unimportant, and the other one makes a big footprint. So no, these things are not of equal magnitude. There are 36 orders between them, and the reason there are 36 orders is because the effect of a bit of space being missing, which is much, much smaller than the thing that makes that missing space. There is the photons in an electron. The photon is inside a box of its own making, and that box is a very, 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 very strong box. It's something which is stronger than the strong interaction. Leptons smash hadrons to pieces when they hit them. They're much stronger than hadrons. So we're talking about something which is just on a completely different scale, 36 orders of magnitude away. So you've got to imagine, chicken and egg, but the chicken is 10 to the 36 times bigger than the egg.
But it operates over a large distance because it affects the rest of the universe also. Gravitation is everywhere, while the field is very localized.
That's right. Gravitation. No, the electric field is also over the whole universe, inverse square, in exactly the same way that gravitation is. Okay, it doesn't normally get that far because your average electron's got a proton nearby. But cancel it. But no, the two things are equivalent in long-range effectiveness.
Is there a difference between the field of a particle, like the electric field, and the space? Is there a separate space independent of the fields in your theory?
Wolf, there are 5 things that go into my theory. That's space, time, and root energy. So yes, the fields are dependent on that thing. The field is a derivative of a vector thing, of a motion. It is dv by dt by d time for the electric field, and it's dA by dt for the electric field in conventional physics, but that the A is a vector potential, so it's a vector derived with respect to time gives you the electric field. The curl of the 4-vector potential gives you the magnetic field. So the fields are derivative in both meanings of the word, in that they are a derivative, literally, of d space by time, or d space by d perpendicular space. So they are not in space and time, they are of space and time. They contain space-time in their nature. They are areal forms, as in areas. So yes, absolutely, there's a connection, but the field is not the thing that's creating space. Space is the thing which the fields are made of.
So it's kind of a duality between gravity and these space-time interactions.
Gravity is a shadow force of electromagnetism. And by shadow here, I mean the same sort of thing that you see on a sunny day when you look at your shadow. If you imagine 3 particles, then so imagine a particle where my nose is, and this particle wants to communicate with that particle, but the nose gets in the way, it shadows it. Now that shadow is really very small because electrons and protons are really very, very, very small. The probability of it interacting is even smaller. But if any photon, so imagine my test electron over here in my left hand. My test electron in my left hand, it's got stuff coming in from all directions in space, continuous interaction with the rest of the universe. So we have particle, and we have the duality between the particle and the rest of the universe. That's like a pressure. So now if I put a particle in the way, that creates a little bit of shadow. And that little bit of shadow, if I have a particle here, that little bit of shadow means there's slightly more pressure coming from over here than there is from here. And that means an attractive force between these two particles, which is what I think gravitation is. It's a little bit of space that is missing. But that's a whole talk. And that's what we talked about briefly in that.
Yeah, and that was, I think it's now 30 years ago.
Yes.
It's going to be really interesting to hear that talk now when you have thought about it 30 years more.
At the moment, I'm holding fire on that because my notes on the calculations for that are 1,000 miles away from me at the moment. And I don't want to do the calculation again because I remember how much work the integral was the last time.
But it's very interesting in philosophical terms, and Wolfgang and I would like to hear it.
Yeah, well,
sure.
We will. You will. You need to wait for a few weeks.
At the risk of returning to the topic of elementary particles, I have a question for Viv. My question is, in your model, do you propose specific experiments that can be done, or is it primarily the analysis of the existing experimental data that can validate?
Well, two things. One, I think they should turn around and try and find that in the 1/27th frequency oscillation of a nucleon. It's about 34.5 MeV per c squared. My understanding from some discussions I've had with particle with someone who knew a bit about this was that they have been detected, but they fall completely outside of, or they were detected earlier, but fall completely outside of the standard model, so they were just ignored. And that what is happening now, you don't think they've ever been detected, John?
Viv, I spent 7 years looking at these damn things and, really looking at them, and there is nothing there.
Nothing down there.
There's not. I think that's so. I think I was going to ask this question later, but I'll get onto it just now. I think the ninth thing is, I think, wonderful, but I think it is a coincidence for the muon. The fact that you don't see the 27th or the 81st or that sequence of things in masses, you would see them. You'd see all of those particles easily.
Well,
because
you do detect their presence in the neutron. The neutron has to have that N27 and it also shows up in nuclear binding when all of these satellite nucleons stick to the outside of a nucleus for fractions of seconds or milliseconds. They all depend upon that particular reaction.
Yeah, no, and I love the fact that you have these resonances within the particles as they exist. But how would you feel? I was going to ask the question a different way. I'll try and now frame it in that way. How would you feel if the 1/3, 1/9, 1/27, and so forth oscillations could only exist as they can only exist on a guitar string if a fundamental was there already and couldn't exist separately? And that the muon was something different, and the muon is a different kind of thing to the proton.
You do have a problem that all of the muon's properties match up with what is predicted, with what is observed. Yes, I agree. It doesn't prove their existence, but it's fairly strong evidence that they do exist.
Oh, muons exist. What do you mean? The 1/3?
No, the muons are 1/9 oscillations in protons and neutrons.
Yes, and that's nice, but it's only one data point. And the fact that you don't see the 1/27 at all, and believe me,
outside you see its effects outside.
But you don't see the thing as
you see its effects inside the nucleon. Yes, you don't see it outside.
Yeah, you see in a high-energy physics experiment, if you produce a muon, it goes through the entire, because it has 10⁻⁶ seconds lifetime, a millionth of a second. It can go a long way in a millionth of a second at the speed of light. So it goes through pretty much, it acts as a stable particle in those things. You can really see it. Now, if there had been anything at 1/27th, I'm absolutely sure we would have seen it, unless it was ridiculously short lifetime, for whatever reason, unless it was certainly less than 10 to the minus 20 seconds. I think less to the minus.
John, why would it need to come off as a discrete particle and remain as a particle? Why could it not come off and unfurl as a photon? You know what I'm saying?
Yes, I know what you're saying, but it would have some charge effects. It would have spin effects. So it wouldn't just. It's not a photon. I mean,
well, its spin effects do show up in the difference between a muon and a pion.
That's certainly also very telling that you have like a 1/9 and 1/27th there. But the fact you don't have the 1/27th by itself means I don't think that the muon is just a 1/9 bit of a proton, a 1/9 resonance of a proton. I mean, it looks nice, but it's only one data point. However, once you get inside the proton and the neutron, and you're arguing about the neutron, I think it's excellent. So,
John, if I might push back on your model, you have a trefoil, and your equivalent of the quarks are three kind of resonant things that cannot exist on their own either.
That's right. Well, that's right. So, and that's why you don't see them on their own. And then the muon, and this I've come back to the proton as well. I mean, in my model, what the proton is it's three left-handed things, if you like, or three right, going in the same sense. And what like three quarks, like three loops, a loop, 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 right, 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 and you get back to a continuous system. Whereas the mesons are things that are figure of eights. They go left round one loop and then go right back round the other loop. Hence two loops and hence two quarks, or a quark anti-quark, in fact, in that case. So I haven't really presented that model very much yet, although I think I did do something on the FSI talk.
Yeah, but one of the things that I have found with a lot of people that they present something which is quite self-consistent within itself, but you've got at the same time, if you're talking about structures of protons and neutrons, you really need to consider how they unite together within the nucleus and all those other properties. And at this stage, what you're saying, John, is that okay, the fact that the n/27 oscillation hasn't been detected outside could indeed be due to its very short half-life, isolated, but all of the other properties it has. But when you're talking about other models of protons and neutrons and muons, you really do need to start. It would be my opinion, it would help considerably if you were able to then go on and show how they are responsible for nuclear binding and the structure of nuclei and all that sort of thing.
You could well be wrong.
Rather than just come out here, I have this wonderful theory about a proton. It needs to be able to say, yes, and this theory is good because it turns around and shows all of these properties of nuclei, or nuclear binding and all that sort of thing, which of course is what I'll get onto in my next couple of talks. And maybe we should have the discussion after that.
I think that's right. I think we should. I've looked at your nuclear binding things already, Viv, and I love them. So I'm looking forward to you getting onto those talks. I think what I'm saying at the moment is that perhaps it is just saying that the meson is like a shard of the proton. You'd expect to see other shards at higher harmonics as well, given the beautiful agreements you have with the over 9, over 27, and over 81 things that you also have for the.
I haven't come across the over 81 yet, but there's no reason why it couldn't exist.
Well, again, it's not. Things at that mass are just not there; they're not observed. No. So these are quite big masses. They're much bigger than the mass of the electron, and you'd see that sort of thing. You'd see it even if it was created just for a moment.
Yeah, but Viv doesn't predict it to be 81, right?
No, so it can exist, but it is not necessary to explain any of the properties of the protons and neutrons. And indeed, it would be so large, it would be tens of FEM, tens of femtometers in diameter, and I can't see how that fits into anything.
Just so that I'm clear, you're saying that the proton has the 3rd and the 9th, and then the neutron has the 3rd, the 9th, and the 27th. That's correct?
That's correct, yes.
So Vivian, I have a feeling that if we spend more time on your slide 13, we might end up in something that is more towards what John is thinking about, more a complex knot or something with more stable internal states with not 1/27, but also 1/3 or even 1 inside
well,
it.
The one is the basic, yes.
One's the basic.
One is that the 1 is detected in the internal diameter. Yes, go back. Can you keep going back, Arnie? Yeah, that diagram. You'll see there in the top right-hand corner, which is the charge distribution of the proton. The peaks correspond to a radius of 0.105 FM, which is the expected radius of a particle of the mass of the proton. So and also you'll see there on the diagram on the left, it shows the P/1 oscillation there in the center. So that is there. It just doesn't exist at all. It isn't the whole aspect of the proton.
What I mean is that there is so much that you might be skipping over, or there might be a lot of things that can be analyzed if you were interested in high energy particle physics that you skip over because you don't need it.
That's right.
And that might lead, yeah. But maybe you can get someone interested in actually make a more detailed look into all those possible experiments that has been seen from all these possible oscillations that you can have in the rotating photon.
Yeah, I agree with you. Look, all I'm doing...
someone else, not you, because you're not interested in it enough.
All I'm doing is providing a sort of skeletal framework for everything. There's an enormous amount of detail that has yet to be filled in, although as this series goes through, I do fill in some of it. Gravity, of course, will have to wait, and even things like...
Exactly what I meant. I'm so happy you didn't get stuck here. You went on, and that's good. That's what we want.
I will admit that I tried at some stage to publish this and got... and this has been going on for over 30 years, got the standard rejection notices because it's not standard model under whatever excuse is used. And rather than try and spend years arguing with referees, I just decided, well, go on and complete the study. And that's what enables me to go and just continue using photons. And of course, John's wonderful equation, which I can't pronounce. D psi g or whatever it is equals 0, just d mu psi g, I think it is, John, equals 0. Sorry, psi, whatever. Using that as the sort of fundamental basis for everything, because theoreticians like to have a fundamental basis of everything, except for quarks and gluons, which they've never detected, but they make very good mathematics. Then just went on ahead and gone from the smallest to the subatomic particles, which you've just seen the presentation of, all the way through to the big end of the structure of the universe and general relativity, gravity, and all that sort of thing, all in one go. And yes, I'm just providing a skeletal structure, but there's an awful lot that can be built on it. And I think people build, my only impression is that if people start building on it in this model, they're going to get an awful lot further, an awful lot quicker than if they keep going with a standard model. I mean, nuclear physics, the first model for a neutron, for a nucleus. Yeah, thank you.
Imagine you could have some of the money for that accelerator going into some PhD students for you. Yeah.
Just a small fraction, yeah. Some of the. Sorry. It'd be nice to have the people too. There's some pretty smart people being swallowed by that process.
Yeah. I make no bones. I'm quite sure if some organization was to invite John and me to work at their institution paying our expenses, because I'm not going to do this for free, but between the two of us, and throw a couple of others in, including Arnie, I think we could get through all of the problems that they have and put them on a very, very firm foundation. And whatever organization did that first would have a significant advantage over all others.
I think what you're going to do next, it doesn't really depend on the correlation you have between the muon and the proton and the neutron. I think the proton and neutron starting point that you have is so solid and so beautiful. Going on from there, I think people will see for themselves when you start to put those together just how wonderful that stuff is. I make no bones.
John, it might be that he's actually correct with it, that this 1/27 oscillation is stable in itself. We don't know because it hasn't been studied yet. So it might be true as it is.
No, Joachim, you're misunderstanding. When you smash a muon at very high energy into a proton, all sorts of stuff comes out. And you see what comes out. And the point is that in the experiment, there's no sign of the 1/27 mass. And really, this would be an enormous cross section. That thing's a nice.
I see. So then that one should immediately fall down to a more stable state, and that's what we see then.
For example, if the thing could be very, very unstable, then there would be an explanation for that. And yes, exactly that. It would have to be very, very short-lived, but you have to have a reason why it's so short-lived as well, because it may be more fruitful to go the other way and say, look, the proton's really 3 by 3 muons, a pair of triples of oscillations of muons that are resonant with each other that go up to the proton mass. It might be better to go around that way. But I think the point is that well, okay, I've made a point already. I don't think you need
you do have the issue that you must always turn around and if you're just talking about muons, you've got to turn around and match the proton's charge distribution, plus the fact that the strong nuclear force is very strong, but has such a limited distance. It's not like it has some decay associated with it. It decays down. It has a reduction, but it reaches a stage where it stops. Unlike the electromagnetic force, which also decays down, but it continues to decay down at a very, very weak amount. This one just gets about 5.5 FM, and there it stops.
It goes off. Yeah, that can be achieved with mass as well. You can have a Euclid potential that pulls it down.
Yeah, I mean you can prove anything you like with mathematics.
You're not wrong.
And they do.
But also, there is also another simplification that might be affected here, that in Vivian's model, it's a plane everything. And really, the particles not themselves as compact as they can be to eliminate as much field as possible in a small volume as possible. And then they're not a plane anymore.
I think that when things are resonant and harmonic with each other, the condition on an isolated particle, there are symmetry conditions on that, which make the thing spherically symmetric necessarily. When you start stacking them together and you have interactions where there's a flow where the particles are not single particles, but they're really states, continuous, resonant, harmonic states of the underlying photon mass fluid, then the things look much more planar because once they start sharing each other in a flow which is going vertically, then what's left is horizontal, and I don't think there's any problem with that. I don't think there's any problem with nucleons flattening stuff up.
So for the photon, when the photons interact with each other, then the interaction happens in the plane. But I mean that plane is not planar. That's what I mean. It can create a knot.
Think about the energies that are involved. The electrons are 2,000 times less massive than the proton. There's a huge amount of energy as you go up to nucleons. So while the electron's perfectly spherically symmetric and structureless in the sense that it seems to consist of only one particle if you scatter from it, the proton is not. The proton has structure. The proton has internal structure. That could be Viv's beautiful wheels within wheels, or it could be quarks, or it has some structure, and that structure is at a much smaller scale, but it's also and therefore also a much higher energy scale. And the energies are so big that taking a round electron and squashing it flat would really be no problem at all for the amount of energy you're talking about here. So, and any other object could be squashed flat with that kind of energy. So I think that while Viv's and my model of what's happening here look different at the level of the electron, I think as soon as you get to the level of masses that we're talking about with the nucleons, they're going to look very, very similar. An electron at high speed looks pretty much flat. An electron at the proton mass is as flat as a pancake at the proton mass energy. A 1 GeV electron looks pretty much identical to a photon in terms of its electromagnetic interaction.
But that's from the observer. From its internal side, it's spherical still, even if it's high speed.
In its own frame, it's spherical, if it's isolated. I think if it probably squashes it flat, though.
So, what about the case of if you did an Einstein thought experiment and had a photon go so close to a black hole that it goes around in a loop? Isn't that increasing the mass, just like in the block? So is really the mass of a photon going next to the sun really that much different than the photon which gets close to a black hole and then ends up going into a loop and adding to the mass of the black hole?
I think the key thing is that anything that's confined to a box, that's within a box. Now, if you think about it, if you measured things fast enough and you had mass in there, which was just a ball bouncing up and down, you'd see dong, 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 dong. You'd see an oscillating mass.
Right.
So if it's sufficient, but if you average that, then that's an mass, which is just the mass of the ball. And the same thing's true for your photon going, or anything else going round and round. Any kind of object, the Earth going around the sun, you see oscillating gravitational fields as the Earth passes close to you if you just sat out there in space. But the mass.
So there's really no problem in thinking of the photon as having mass because of its gravitational pull towards either the sun or a black hole.
All of these things are consistent with ordinary physics and ordinary relativity. Yes, there's no problem.
I give plan to give a talk later, Pete, where I do turn around and say that all of the relativistic effects and more that are predicted from Einstein's gravitational field equations actually come from using Newtonian mechanics on the mass of a photon. And the only thing, and when I say predicts more, it turns around and gives explanations for fact, like it gives explanations. Its explanation for the precession of Mercury's perihelion is, as Newton pointed out earlier, that if he only predicted inverse square law, if the planet always returned to or under the inverse square law, a planet would always return to the same point in space. But if gravity was less than inverse square law, he would have a precess. Now, if you use the mass of a proton and apply Newtonian mechanics to that, and then you'll find, and then you use Einstein's mass distort space-time, then the space-time is the redshift. You add the redshift to it, and you get, in my calculations, the predicted precession of Mercury's orbit is 42.99 arc seconds per century, whereas what the Einstein's theory predicts is 42.98 arc seconds per century. And as I say, I'd sure as hell hate to try and make a difference of a living off that difference, but that's what we're trying to do. And when I get through that, then you'll start to see that yes, photons do respond to mass. The mass of a photon is different, and the mass of a photon on the surface of the sun is because, and it's just a potential energy difference between the surface of the sun and where we are, is 2 times 10 to the minus 6, which is the redshift from it.
And all of that's explained in a talk which is up on Quicycle, if you want to have a look at it. It's one of the quantum precession of the perihelion of Mercury by Viv last week.
John, we've been going about an hour. Probably good time to start wrapping up.
Well, thank you very much, gentlemen, for listening.
Thanks very much again to you, Viv, as well, and we'll look forward to next week's exciting episode.
Okay.
Thank you very much.
The week after that's going to be really important. That's the one where we'll turn you all into instant nuclear physicists. Cheers.
That process, I hope, is not painful. I'll see you later.